Hey everyone, thanks so much for checking out my second interview with Etienne Dilocker from Semi Technologies and the Weaviate Vector Search Engine. We're developing new podcast content, also working with Dimitri Khan from the Vector Podcast to bring more podcast style content to YouTube and particularly around vector search engines. So we're currently thinking of maybe having the Weaviate Podcast on the Semi YouTube channel and maybe going for kind of the flair of the Stanford MLSys YouTube channel and having a revolving door of people who want to come in and discuss ideas around vector search engines. So I also highly recommend checking out the Weaviate Slack channel. This is a really great Slack where people post very specific questions for their use cases with Weaviate. Debugging errors sometimes are in there also, but mostly ideas about how to use the vector search engine and how to add new features to it. So most of our questions and our topics for our interview are sourced from the Slack channel, and bringing these topics and discussions from the Slack general chat into the life of the podcast. So we're going to be going deep into the HNSW algorithm as well. I made a ton of leaps in my personal understanding of it from just picking Etienne's brain about these topics and getting to understand how the HNSW small world graph structure helps facilitate vector comparisons for speeding up vector similarity search and vector search engines. Before Etienne and I dive into the details of HNSW and miscellaneous topics that came up on the Weaviate Slack channel, we're going to talk about the Weaviate console and the interface to have the GraphQL API to use the web interface to start playing around with these neurosymbolic vector search engine queries without having to really download your own dataset or set up your own Docker container. So for example, Papers with Code just released the Medical MNIST version 2, and they've been organizing datasets that are commonly used in deep learning, things like CFAR10, ImageNet, MNIST, and all these things that I'm sure everyone watching this video are pretty familiar with by now, things like Squad and Glue. And so the idea behind the Weaviate console is going to be you can just one click onto any of these data sets like MNIST, just click and you're in MNIST, and then you'll be able to do image similarity search, or with these text data sets like Squad, or maybe these just Wikipedia text, you'll be able to do vector search purely on the internet without having to download anything. So the first topic that we're going to get into in this podcast is just a clarification about the Weaviate console and just trying to help more people understand what's being built and how this is going to help people quickly explore these data sets used in deep learning and the capability of vector search engines with this front-end web GraphQL interface. So with that said, I really hope you enjoy this podcast, and if you like it, we'll be having more content rolling out soon and figuring out the format of how we want to develop this kind of vector search engine podcast content. So just to further clarify before diving into it, we're talking about this front-end web demo that can be used for any data set. And currently what you can use it for is news articles. News articles is currently the endpoint that's hosted, and many more data sets are being added. So you can just run these vector search engine queries with this front end without having to download any data sets. And we're working on trying to integrate this with the massive collection of data sets. You see Hugging Face data sets, Papers with Code data, and things like Kaggle that organize these data sets and then let you just quickly explore the capabilities of vector search engines right on the internet. So with that said, hopefully it's very clear what we're talking about at the beginning of the podcast, and then we'll get into details like the HNSW data structure and then Slack topics. Hey everyone, thank you so much for checking out the Henry AI Labs YouTube channel. This is going to be the first episode of a new series called The Vector Search Show with me and Etienne Dilocker. This is going to be like an office hours with Etienne where I get up to speed with all the details of the Weaviate vector search engine, miscellaneous things like the HNSW search index, the details of contrastive learning for vector encodings, and all sorts of other things from model inference load balancing to just all these different issues that we see that come up in the Slack chat. So this will be a detailed podcast going through the technical description of these algorithms. We have a premeditated list of topics, so it's not just going to be like free riff rambling. We're going to be drilling into these different ideas and really clarifying what we mean by these ideas, like applying neurosymbolic filters to the vector index in the HNSW. And a lot of these topics that we're finding are sourced from the Slack channel on Weaviate. So if you're interested in contributing to this podcast or having your questions heard on this podcast, then please check out the Slack channel. So Eddie, do you want to say anything more about the engagement of the Slack channel and how that's kind of organized?
Yeah, it's a relatively small community, but I think it's a very high quality community. So what we're seeing is that since Weaviate is an open source product, anyone can use it. You don't have to pay for it. You get the documentation, of course, but sometimes there's questions like, especially with regards to the roadmap, or if there's maybe a performance issue or something. So we have the Slack channel, and I think as of now there are about 200-ish people on it, and it's rapidly growing. But it's such a nice community because we see people are helping each other out, and people aren't just there to like say hi and say, hey, what is Weaviate? But it's like everyone seems to have worked with Weaviate and they have very specific questions. So it's super cool. It's super cool for us as a feedback channel. It's cool, I think, for users because they get help either from us or from other users. Yeah, can really recommend it. And it's a very fun to see it grow.
Yeah, I definitely recommend it as well. For me, getting up to speed with Weaviate and coming into the Slack, it just like Etienne just said, there's specific use case questions, and it's really great for helping you understand the ins and outs and the details of it. So to kick off our Vector Search Show podcast, I wanted to just get a little more question about the web demo. And this is something that I've been trying to push. If you've been watching the Henry AI Labs videos, I'm sorry if you're sick of hearing this, but I think it's so important for people to see the web demo. You have a web front end that you can do these GraphQL queries with. And we've seen a recent trend in deep learning where we've been moving data sets to say Hugging Face data sets, or as you know, the Kaggle competitions, Kaggle data sets, and also papers with code, papers with data. The organization of these data sets that we're using to benchmark these models has been a really key driver in progress and key for, say, new students, people interested in these algorithms. So I'd really like to see more and more adoption of, say, we have these Streamlit interfaces where you can do almost like a pandas df.head of a lot of these data sets. And we're trying to push these endpoints for vector search engines that you can just click on the internet, and then you can do vector search, neurosymbolic vector search without having to set up a Docker image, without having to download the data set. And you could be able to just click around the data sets, similar to Hugging Face data sets, where you get to just click on all these data sets and get a quick sense of what's going on in natural language processing. We're trying to build that same kind of idea with these neurosymbolic queries. So let's start off with the interface of the console.semi.technology. When you first go there, the options that you see are to log into the cloud service, or you have the self-hosted option. Could you tell us a little more about the background of how this came to be and how this interface is set up for people to check out the web demo?
Yeah. You already mentioned those two options. You can either log into the cloud service, which basically means all the infrastructure is abstracted away. You create an account. It's completely free. I think there are also, I'm not sure if there are paid offerings at the moment, or if we definitely plan to have paid offerings in it as well. But basically the idea is you don't care about the infrastructure. You just tell the cloud service, okay, I need my Weaviate instance, and you could either start from scratch, or you could also preload stuff. But in this sort of, you would still start from scratch. Probably you would start with, there's nothing there. You log in, and then something is created. The second option that we have, and I think you already raised that point in our Slack last week, that currently it's labeled self-hosted, which might be a bit confusing. So the idea behind it was that option A is the cloud service. Option B is really just, it doesn't matter where it's hosted. You just put in the URL and then you connect to it. And this can be sort of either the machine. So the console is running in the browser, which is really nice. It's completely a JavaScript based app. So you can connect to something you have running on your local machine. It doesn't have to be exposed over the internet. And this is a sort of very typical case that we see, which is, people started out. And then, of course, you have the GraphQL API, and GraphQL has this autocomplete feature and these kind of nice things which are accessible through the console. So the first thing that users would do is go into the console and put in like localhost 8080 and connect to that. Now there's also a third option that personally I haven't thought so much about, but I think that's sort of the most natural one for you that you mentioned, which is just put in one of the demo instances which already have data deployed. And I think we saw the news publication one in your recent overview video. And for this, the name self-hosted might actually be a bit confusing, because of course that's not self-hosted. It's just run somewhere. So yeah, this might be worth rethinking these options. Maybe even add 3 options that we say cloud service, pick one of the existing data sets. And right now, I think the news publication is the only one that's constantly running, but we're just building the Wikipedia data set as well. And there's also one about Wikidata. So there's definitely more coming. Yeah, so either cloud service, pick one of 3 existing, or connect to any URL. And the any URL could also be one of the existing ones, but most likely it's going to be whatever the users are running locally.
Mm-hmm. And so right now there's just the news articles, or you have publications, news articles, and authors, but pretty soon there'll be the Wikipedia text data, in addition to the PyTorch Big Graph with the free base embeddings and really exciting stuff. Me personally, I've known about graph embeddings, things like Deepwalk, Node2Vec, and we'll talk later on in the podcast as well about knowledge graphs. But I think Weaviate is really helping me personally understand knowledge graphs. And I think listeners of this podcast, as you get to understand this kind of idea where you're putting these massive text data sets within these kind of noun entity relation schema. And I think once you kind of study this, it'll help this concept of knowledge graphs click more for you, or at least it did for me. So awesome. So that's really great. I'm really excited about this web demo and maybe setting up just like clicks where people can just click onto these data sets and be taken right to the console. And this console, again, is like this front end interface for the GraphQL. So as Etienne mentioned, you might have your own personal data set that you host with this endpoint, and then you have this like GUI to play with the GraphQL. So really cool thing, and I'm really excited about it. So now let's transition into HNSW. Going to try to tackle the beast and understand what's going on with this thing. So let me start off with the ANN benchmarks. To me, I see ANN, I think artificial neural network is what it stands for. So what's going on with these ANN benchmarks?
Yeah. So the ANN in this case is approximate nearest neighbors, which it's very unfortunate that you have like a 3-letter acronym or a 3-letter abbreviation, and then it has 2 meanings. I know it is approximate nearest neighbors. And really for me, what I like the ANN benchmarks website is really, it's a comparison of algorithms. So for example, you have HNSW in there, and I think HNSW is in there like 2 or 3 times because there's the reference implementation from the authors of the paper. Then you have, I don't know, I think Facebook's Face has its own HNSW implementation. Not entirely sure about that, but I think so. And you have other vector databases. So for example, I think Vespa, they also have their HNSW implementation in there. What's super interesting about this, or maybe just before I get into those, let's just say what it does. So typically, it just shows you the trade-off that you make with those approximate nearest neighbor indexes, which is basically the higher query speed you want to have, or the higher either query per second or the lower latency you want to have, the worse your recall becomes. So if you start out with a brute force search, you have a perfect recall of 100%. But your queries per second are going to be very low. And then sort of as you move in all these algorithms, so it's for comparing one algorithm to another, but also within a algorithm for comparing different build parameters and query time parameters. So for example, in HNSW, to make it a bit simpler, if we completely pretend that there are no build time parameters, if you only look at search time parameters, then we have a single parameter left. This is this EF parameter. And essentially, if we use a higher EF value, the search takes longer, but it gets better. It reaches more. So if you take a sort of looking for a limit of 10 result, so K equals 10, basically 10 nearest neighbors, but you're putting EF at only 10, it can never be lower than K. So 10 would be the minimum. It would be super fast, but the result quality just wouldn't be very good. So this is one of the simplest trade-offs that you could do in HNSW. Well, instead of putting it to 10, let's set it to 100, and the search is going to be ever so slightly slower, but the quality gets better. And then typically what we see is that people target within the sort of 95-ish% of recall. And of course, that's completely dependent on each use case. There might be cases where you say this really has to have perfect recall, and it's okay if it's not as fast, or the other way around. So this is what the algorithm does in general, or sorry, what ANN benchmarks does in general. Something that I find interesting in there as well is what we see is really the algorithms itself. So these are typically, I think this runs from a Python script in Docker, but basically you have everything in memory, you import everything, and you run it on the exact same sort of on the exact same code base, or within the same software process, basically. If you use a database, and this doesn't have to be a vector database, just in general, you have, for example, a network connection that goes from your host machine to that database, even if it's running on the same host, but you still have an HTTP connection, which with these algorithms being so fast, so some of them have response times, depending on the recall, of less than a millisecond, let's say, I don't know, 2.5 milliseconds. Most likely the overhead for the HTTP request is going to be higher than that already. So this is something that you need to keep in mind. If you have a fast algorithm such as HNSW, in real life, when you have this deployed somewhere in production, probably with a vector database, but even if you were to just deploy the library, you're never going to get sub-millisecond response time, simply because there's more overhead to be done. So this is also one of the reasons why you won't find Weaviate, for example, in the ANN benchmarks, because it would just be comparing apples to oranges. However, HNSW is an algorithm in there, and then you can just sort of draw your conclusions. Okay, if under these sort of very controlled conditions, this is what HNSW can achieve, then I know, okay, it's among the better ones. And then you can say, okay, if I use a vector database that uses HNSW, and I trust that their implementation is correct, then I know that, yeah, roughly sort of these are the kind of speed recall trade-offs that I can make.
So viewers on the screen, we're looking at the ANN Benchmarks website right here. And what Etienne's talking about is the comparison of these algorithms shown on the right in the legend. So you have the HNSW in the light blue from the face, and you have the gray HNSW, and I'm not sure what the implementation is, but another HNSW. So we're talking about these different algorithms and comparing them for approximate nearest neighbor search. So before we get into the EF hyperparameter on HNSW and the small world graphs, and we're going to get into all those details, first let's just take one step up to the data sets that we're looking at. So we see GLOVE 100 angular. I'm assuming angular means angular distance between vectors. We have GLOVE 25. We have LASTFM. Could you maybe tell me a little more about what these? And then we have fashion MNIST. So how are these? How's the ground truth annotated? Is it you're finding the exact match in the data set? So say you have the vector for a fashion MNIST sneaker or bag or the things in that data set. Are you giving the vector that exactly matches one of the data points and you're trying to exactly match it? Is that how this is measured?
I think you would do a nearest neighbor search around one of the elements. So I think if you have, for example, 1 million objects in the database or a million vectors, because sort of, yeah, when I talk about objects, I think about a database, of course, but in those benchmarks, there are no objects. These are really just vectors, and maybe they point to an ID. So I think for each, yeah, let's say you have 1 million vectors in there, and then you have maybe 1,000 queries, and then for 1,000 queries, you would have the ground truth of 100 neighbors. I don't know if it's actually 100 or not. I'm making this up. But then for those, you would have the ground truth defined, and then if your algorithm returns, I don't know, 98 out of those 100, then the recall for this particular query would be 98%.
Got it. And it sounds very similar to, say, information retrieval benchmarks, like the BEIR is a recent one that a lot of people think is really cool. So do I. Not that, but so yeah, it sounds a lot like information retrieval. Do these benchmarks take into account the continuing update of new data points, so like the increment? Because it seems to me like not only is it important to have it be this static data store, you also want to have different algorithms that adjust it. And next, I'm going to transition into kind of comparing this to like a binary search tree and that kind of idea of searching. So is there an incremental benchmark, and do you think that would really add any value, or am I reaching with that?
So from what I know, there isn't. So what you're saying is absolutely correct, that these are entirely static. And the good thing about this is it opens up the door for many algorithms, because a lot of algorithms aren't even capable of incremental buildup. So basically you build them and then you can do searching, but then you can't change them anymore, which is, I think we talked about this in our first podcast, not from the show, but our first time that the two of us were in a podcast. Yeah, we talked about why we, as the developers behind Weaviate, chose HNSW, because one of the things that you can do with it is that incremental buildup. So yeah, the advantage of not having that in there is that you can have algorithms such as Spotify, Annoy, and Google Scan, which, as far as I'm aware, they don't support the incremental buildup. So that's the benefit to that. Is there a benefit to also verifying this on an incremental setup? Absolutely. So this is, I think, something that where probably you will see different vendors of vector search engines sort of having their own benchmarks. I know that we have something where this goes in a slightly different direction, but there's some overlap. So we have a benchmark, for example, where if Weaviate were to crash during an import, and it would then sort of recover from the crash. So it could be any kind of, could be hardware failure, could be because it ran out of memory, or all these kind of scenarios. And then basically we wait for it to come back up and we continue the import. And then in the end, we validate that everything still makes sense, or even just a single sort of, yeah, you import, you have a crash, and then you validate after the crash, which wasn't a controlled snapshot, so to say. So you don't sort of build it once in memory, then have a graceful shutdown where you can store the snapshot on disk, but it was crashing all the time. And as a database, we have these mechanisms to prevent against that. And then we have those, I wouldn't really call them benchmarks. They're basically just quality gates in our CI pipelines to make sure that, yeah, Weaviate can handle these kind of situations.
Awesome. So let's now get into the beast of the HNSW. And so with the incremental buildup, this is kind of reminding me of, say, red-black coloring, where you had to balance binary search trees. And so HNSW isn't quite a tree. It's a graph structured thing, and you're going on the idea of network science with small world graphs. And this is communicated with ideas like, if you watch these videos on an introduction to small world graphs, they'll say, how many hops away are you from, say, Barack Obama? And you'll be surprised that usually it's only like 6 or something like that. So how does small world graphs work with this? How do you build this up? I mean, I'm not asking you to explain the whole algorithm in 2 minutes, but how does these
Let's see if
small
I
world
can,
graphs?
because it's
Okay,
it's actually quite simple. I mean, I probably can't explain it in too much detail, but let's try. So in general, as you said, the graph is basically just if you only have 3 objects and they have a distance, so there's a distance between each object, and basically you have to figure out that distance once, and then you can place them in some sort of a relation. So let's say you have a linear graph with 3 elements. You have A, B, and C. And then if A is closer to B than it is to C, then most likely the chain would, let's maybe call it chain. The chain would go A, B, C. So pretending that this is this sort of one-dimensional graph, if you now get an object D, where do you insert it? And the idea is that you just check what is it closest to. Is it closest to A? And maybe to, or does it fit between A and B? Does it fit between B and C? Does it fit between, we don't have anything beyond that yet. So that is where you would want to place a new entry. And in my example, it's just this line. Sorry if I need to put that glass over here. Don't hit it. In my example, it's just this one-dimensional scale basically. But of course, you can add more dimensions. So if this is close to A and C, you can just connect it, and now you have this 2-dimensional graph, basically. And this is the entire idea in HNSW, because if we come back, if you know where position A is and you quickly want to get the nearest neighbors of A, all you have to do is follow the outgoing edges from A, and you see, okay, B is a connection and D is a connection. So you now have the 2 nearest neighbors. And if we go sort of the extreme case, where you always have all nearest neighbors defined, well, then you end up with a graph where everything is connected to everything, which in theory is good, but that also means what are the nearest neighbors? Because if you just connect everything to everything, well, everything is a neighbor, and then you sort of need to check everything again, and you lose the idea. So there you try to introduce some sort of a cutoff where you say, okay, a neighbor or a node in a graph can only have, let's say, 50 connections. And then I know that these 50 connections are probably the nearest neighbors or very close to the nearest neighbors. And I have to check those. And of course, what you can do is after you've checked something, you can, for each of the neighbors that you found, you can check their connections again. And in HNSW, they call this the heuristic 2, I think. That was from the paper. I like this name. It's like how software engineering goes. You just label something, you put a 2 on it, and then it sticks around. And this heuristic 2 basically trims down connections. So whenever you add a new connection and you have too many connections, then what you do in this case is really say, like, does this new connection add value? And the definition of does it add value is, if we stick with this ABC, if this is a neighbor of A, but it's actually closer to B than it is to A, then I don't need to connect it to A itself, because I know that it's just 1 hop away. And this is exactly the small worlds thing that you just mentioned. Like, you wouldn't have to personally know Barack Obama, because you know someone who knows someone who knows someone. And then the idea is, by sort of making use of those hops, you can sort of keep the connections low. And if the connections are relatively, or keep the connections few, if there are few connections, that means you have fewer connections to check at query time, which means it's faster. And of course, you have way less data that you need to store, because these connections add up. Like if you have 1 million objects, each with 50 connections, that's already 50 million connections. And then one connection is probably a int64 ID or something. So you have 50 million times 8. So you have 400 megabyte or something already. And don't know if that calculation was correct, but yeah, they add up. So there is value in keeping few connections.
Okay, very cool. So let me just quickly backtrack just to ask a couple of maybe dumb questions, but just from my understanding. So the generalization from scalar to vector distance when we're building up these data structures, is that problem, like, because I feel like you have all these dimensions of the vector, so it's not like a binary tree where you can just say, greater or less than 8, yes, go this way. So you have like an angular distance. Is that the threshold? Is there maybe like a baseline, like a 0 vector that's used to do these threshold distances? So you have some kind of reference point for the sake of doing the vector distances?
So what kind of distance? The algorithm doesn't care. You can actually use, for example, geographical distances, which I guess is just Euclidean distance in the end. But you can use any kind of distance metric as long as you can calculate the distance between 2 points. So this is so if you assume you have this massive HNSW graph, and now you need to start somewhere, then basically you just pick a random point, and it's not actually random. It's because of the hierarchical system, it's smarter than random, but for now let's just pretend it is. You start somewhere, let's say in the middle of the graph, and now in the middle of the graph you have these long connections going in each direction basically, and these are just other data points. So you just check what these points are, and because it's a graph and not a tree, it's not sort of a tree has a beginning sort of, and you start and you go, as you said, either left or right. But in this case, it's a graph, so it can have any number of connections. And you just, for these connections, so let's say your random data point that you picked has 3 connections. It's point A, point F, and point, I don't know, G. Then you check the sort of query that I'm searching for. Is it closer to A? Is it closer to F? Is it closer to G? And then these different, assuming these are not the same vectors, one of those will have the lowest distance. So let's say the lowest distance was G. Then you jump that edge and you say, okay, my new entry point is now G. And now you know you're closer to your query vector than you were before. And then you just repeat the same pattern, G as connections again. You don't have to check A because this is where you just came from. Or no, sorry, it wasn't A, I don't know. The random one, we didn't give it a name, I think. But there are new neighbors now, and now you can check those. And you basically make these very large hops in the beginning, and very quickly you'll start getting very close to where you actually want to go.
So the centrality of a node, how many it's connected to within a certain distance threshold, and that could be L2 distance threshold, say 10 arbitrarily, that's how you propagate up the levels of the graph. So let's call it X connected to AFG, and then let's say AFG, they all have no neighbors. X has 3, so it goes up to layer 1, and then layer 2 is AFG based on the connectivity. Is that a correct understanding?
So for now, in my example, I've basically pretended that there's just a single layer. So just because you can, if you ignore the layers, you can do all of that if there was just a flat graph. And then the layers is really an idea that on each higher layer, you have fewer and fewer points, which really that just means the distances, the length of an edge becomes longer. So basically, let's say on layer 0, you have these 100 elements, and you start at the very right side of the graph and you want to go to the left side, then basically you have to check a neighbor. It goes a bit in that direction, check again, check again, check again. And then you'd have to do, say, 10 hops. But now if you have a higher layer where there's only, let's say, 2 elements, one is very much on the right of the graph and one is very much on the left of the graph, and then you start on one of those, then if you say, okay, the left one is closer because they have the same sort of, each element has the same position basically that it would have on a lower layer if it exists on a higher layer, then you can make this large jump, let's say, to the left of the graph. And then you say, okay, now I'm at the best possible point in this graph. Now let's go down another layer. And now you're on the layer where there's a lot of data, but you've basically eliminated the right half of the graph. And this is sort of where it gets similar to a binary tree again, because you've already made that jump on a higher layer. So now you're basically starting with a better entry point on a lower layer and just need to check around those.
To summarize it with an analogy, if it's a social network graph compared to vectors and their distances, you'd say like the popular people are up top and they take you to everyone else with the, say, 6 hops to Barack Obama kind of analogy.
I'm not sure if it's entirely correct, because the popular people would probably just be the ones that are more well connected. Whereas in sort of a higher layer, it's less so much the people that are well connected, it's more the people that know someone on a different continent. So basically you would go to okay. I don't know, you have that friend who has a friend in Europe, in China, in the US, and all of those. And then basically you would first ask that person and they would say, oh yeah, I know where you want to go. You want to go to Europe. And then you make that large jump basically to Europe. And then you start sort of asking people in Europe. And in the end, I don't know, you end up in a nice cafe in Italy or something like that.
So it's more like centroids and like a k-means hashing, where like coverage of the space is what each layer represents more so than.
Yes, I think that would be accurate. We're basically on a higher layer you try to cover a lot of distance, and on a lower layer you try to sort of be more precise.
Okay, so now So now here's what's kind of breaking my brain is thinking about how you can apply a symbolic filter on one of these vector distance graphs. So again, we have this hierarchical vector distance graph where each layer are the centroids that cover the space to the bottom, and then you have a small world connection through these kind of centroid hierarchies. So to me, when you add a symbolic filter, and symbolic filter to say you're filtering the vectors based on, say this is a vector of representations of news articles, and now you add the symbolic filter that the word count has to be greater than 1,000. How do those two play together?
Yeah, this is from an engineering perspective definitely a challenge, and I think one that we've solved relatively elegantly, because as you say, you have this problem like in the graph there is no information about the as you say symbolic data, because we know we have a data point and we know it has those edges, and we know the distances, or we can calculate those distances. But there's basically no relation to the object itself. And one thing that we could potentially do is whenever we are on such a node, we could just check, does it match the filter? Like we could say, okay, this point in the graph results to some object, which is most likely going to be on disk, because you're not going to hold your entire database in memory. So you basically make a jump, you read something from disk, you check, is it eligible? If yes, that's okay. If no, basically you keep going. That would be a primitive approach that would work, but it would be very, very slow because you're doing all these disk reads. So what we've done is basically we said, well, how does a traditional search engine does that? So if you spin up Elasticsearch or Solr, it is very good at those kind of filter questions. It doesn't have the capabilities for vector search, or it doesn't have the capabilities, at least for combining vector search. There are plugins for traditional search engines, but it's very different, a very different approach than an actual vector search engine. But what they do is they use these inverted lists. So essentially you sort of turn it around. Instead of storing an object by its ID, you actually store it by the values of the properties. So you would say if you have an object where the publication journal is set to whatever journal one, you know the journals better than I do. I just call it journal A or journal one. Then you would have an entry in that inverted list file where you say, okay, journal 1 is contained in object 7, in object 9, in object 12, and these kind of things. So that's why it's called an inverted list, because instead of storing the object with its property, you store the property with the objects that match that property. And then you have a very simple lookup list. Sort of finding the property on this inverted list is relatively easy, because the list can just be sorted, and then it's just binary search or any kind of mechanism to find an object on a sorted list is definitely a logarithmic complexity. So that's very quick. And then once you found that, you basically just note down the ideas, the IDs of the objects. And this is what we're doing with the filtered HNSW search as well. We're saying at first, so it's basically a two-step process. At first, we use the classical inverted list just to find which objects are eligible. And then we build this list up of eligible objects. And this is if it's typically what we see is that filters is somewhat restricted. Like people don't set filters if they want to match 99% of the data set. So usually you cut down the space quite a bit, and then you would say out of 1 million objects, 100K, for example, are on this allow list that I've just built. And then all that we have to do in the HNSW search is basically the same thing as we did before. And we still evaluate those connections. So even if we jump from X to A, F, and G, if A, F, and G are not on the list, we still go there because they might be closer to something that is. So essentially, we still use those edges in the graph to jump or to move around the graph. But in the very end, when we return the results to the user, basically, we just discard those that aren't on our list. So let's say we've jumped around quite a bit and we only have 8 matches, but we're looking for 10. That means, okay, now it's okay to accept a higher distance in the graph and basically move away from where we want to be ideally to find enough neighbors. And that way, you basically just keep going and keep going. It's similar to increasing the EF search time value. You basically just keep going until you have enough matches that are allowed on the list, basically.
Okay, so I'm sorry to slow this down a bit. I got a little lost. So step
one.
Yeah,
sorry for going too fast.
No worries. All right, so step one, so we have this inverted list where we say the publication equals New York Times. So now we have the vectors of the articles that were in the New York Times. So we're not rebuilding an HNSW graph from this subset of the vectors. We're still using the original HNSW graph.
Yes, exactly. Just we're basically discarding some of the elements in the graph.
Okay, so we pop all the nodes out of the graph that aren't in this filter. And now we're just so by popping all those nodes in the filter, when you look at the neighbors of a node in the graph, it's a smaller cardinality set, and then you traverse it faster. And is that the big idea?
No, it's actually it's kind of the opposite way, because there's two kinds of states for one of the neighbors. Like, is it closer to where I want to go? That makes it a good candidate. And is it allowed to be on my result set, basically? And if I want to get closer to my query, to my search query, which is the goal of a vector search, I still need to follow those candidates that are closer to the query. So I'm still going to follow them. I'm still going to evaluate their edges. Just out of those that I find, the question is, can I use it? Yes or no? And that set gets smaller. So the search time actually goes up slightly, because we might evaluate, let's say in a typical case, in an unfiltered search, we have to evaluate, making this up, 5% of the entire graph to find a good result. So in this case, out of the 5%, we might not have found enough matches that match our list. So we might need to increase it slightly to, say, 6%, and then we find a match. So this is why, as the filter gets more restrictive, the search time goes up.
Okay, so I think I'm starting to get a better sense of the trade-off with the recall and the query speed. So can you explain a little more about this K parameter?
Yeah, K is just the limit, basically. So what we call in Weaviate the limit is just the amount of object that you want to return. And then you have EF, which is basically the number of candidates that you hold at each point. So if you start somewhere, the first set of candidates, so again, random point, we start at point X. The first set of candidates that we have is just its neighbors. Like X has neighbors A, F, and G. So this is basically, at this point, we could return our search and say, well, the closest neighbors are are A, F, and G. Since this was a randomly chosen entry point, most likely these are not going to be very good results. So what we now do is we look at each of those neighbors and evaluate their neighbors. So we're looking at A, looking at the neighbors, looking at F, and their neighbors, which, if they each have 3 neighbors as well, then we would now be at 9 candidates. And out of those 9 candidates, basically, this list could potentially keep growing and growing and growing. And if we had no cutoff parameter, at some point we would just evaluate the entire graph, and it would be as slow or possibly even slower as a brute force search, because, well, we've just compared every vector to every vector, and then it's a brute force search with the overhead of traversing a graph. So in this case, we need some sort of a cutoff parameter. And in HNSW, one of the mechanisms that we do is basically we say, if adding a new neighbor no longer gets us closer to the query, then it doesn't make sense to add it. So let's say we have 100 candidates on our list, and this doesn't matter, so I'll get to where that 100 comes from, but let's say we want to return 10 results, and we currently have 100 candidates on the list. Then if adding 101th candidate doesn't improve the distances in that list, then we know it doesn't make sense to continue, basically. And there are going to be errors in this, because, well, it could be that, yeah, this new candidate isn't as great, but maybe the next one would have been. So at some point, the cutoff is basically where we lose a bit of quality. And this is what makes it an approximate search. So the trade-off is, do I keep traversing the entire graph and get perfect results, or do I cut it off? And this EF value is just the length of those candidates. So how many candidates can we look at any one point in time? And so if we're looking for 10 results, we might say, okay, we're willing to look at 100 candidates. And then if we increase that window to 200, then it would be slower, because we just evaluate more candidates in total, but we also increase the likelihood of finding the elements that we want to look at.
So within the EF set, which is the total number of nodes that we are holding in memory as we're traversing through the graph, we're going to calculate, say, a min max distance from the query within this set. And then as we go along an edge from, say, the frontier of our graph search, like sort of like a breadth first search kind of thing, or that kind of thing, we're going to be comparing it with this minimum or maximum distance that we're storing from our current EF set. Is that correct understanding?
Yes.
Okay, awesome. Okay, so I think we're ready to transition into Etienne's latest article published in Towards Data Science, Effects of Filtered HNSW Searches on Recall and Latency. So you'd give us the TLDR, and then we'll take apart some of the.
Yeah. I think we've already talked about a lot that was in there, which is basically when we apply the filter, what happens. And one of the things that we saw, so there are two things, and one is something that initially we just didn't know. We were just sort of say, if we apply those filters, the question was, does the quality ever degrade? And this is something that we found out that that's not a problem. So the only effect that you get from applying filters to HNSW is the query time. And this is where we introduce this what we call the restrictiveness in the filters. And that basically just means if the filter matches a restrictiveness of 1%, would be the filter matches 99% of the data, as opposed to 99% would be it only matches 1% of the data. And this basically showed us that sort of, in the graph, we keep traversing the graph and we keep finding elements that aren't allowed on our list. So we have to traverse more. And for the most part, this is not a problem whatsoever. So for 95% of the spectrum, this is entirely fine. And then as we go to those edge cases, the query times go up like exponentially. So this is one of the graphs, maybe you can show it, where if there was no cutoff, essentially HNSW, as the filter gets really restricted, the times go really up. But now the cool thing comes in when we're talking about a really restricted filter. What that means is we're just looking at very few elements. And if we're looking at few elements, well, then just comparing every element to every element in the set, essentially your brute force search, is very efficient again. So this is basically the main point of that article. We have these two graphs, one where the query time goes up as we move to the right, which is the HNSW search, and we have the brute force search where the query time goes down as we move to the right, and then we overlay them on top of each other, and basically where they intersect is, and this is a new feature that we're introducing in Weaviate 1.8, which is automatically cut off and switch from one type to the other, and basically doing this, we guarantee that over the entire range of filters, you have a good query time.
This is the graph that Etienne is discussing in the article. On the far left end, we have an 100% restrictiveness, meaning that the entire data set is included in the filter. So we see how the HNSW shown in green is being compared to the inverted index shown on blue. As we go to the right and we have, say, 1% of the data set is included in the filter, the HNSW running time shoots up exponentially, whereas the inverted index time goes down even more because now it's reasonable to do a brute force kind of comparison. So the new feature that's coming in Weaviate is the automatic switching between HNSW and inverted index based on how restrictive your symbolic filter is on the data set. So this is only for...
sorry for the interruption. Yeah, it's just a minor correction. So the inverted index is actually always in place because we need the inverted index for just to find out what is eligible, which candidates are eligible. So the graph that I was talking about where we do the cutoff is, I think it's further down in the document where we have one where we just do a brute force search, which would go down linearly, basically from left to right. And this is what we're switching between. So this one still contains the inverted index, but just as HNSW goes up, we're switching to the brute force search.
Got you. Sorry to leave that out. I did understand that. I'm sorry. I got you. I understood that part. Sorry for leaving it out of the quick description. But so this is only for pre-filtering, right? Or is this for both pre and post?
No, this is only for so currently we're only doing pre-filtering because we don't see any kind of value in post-filtering. I think the only value that you would get from post-filtering is if pre-filtering is not fast enough, but that's not the kind of approach we would like to take. Like if we run into any kind of performance issues with pre-filtering, we want to optimize that as opposed to switch to post-filtering. Having said that, there could be some extreme cases where so just to explain me what the problem is with post-filtering, you do your vector search first and you say 100 objects, my limit is 100, I want to see 100 objects. And then you apply your filter. And if out of those 100, only 5 happen to match, you're just left with 5 results. Those 5 results will probably be correct, as good as the search was. But yeah, you ask for 100 results and you're missing those. And sort of as it moves more in that direction, this becomes more and more problematic. So this is why we don't see a lot of value in post filtering, or to put it in a different way, like post filtering is the easier way to do if you have no alternative. But because we have pre-filtering, we don't see a reason of why someone would use post filtering and would rather optimize the process for pre-filtering.
So the bottleneck is almost always the vector search part and never the symbolic part. Is that because that's kind of the difference between pre and post, right?
The speed bottleneck at the moment, it depends. So if we go to those super restrictive queries, then yes, it's the HNSW index. But we're also seeing that sort of as the data set grows, the inverted index basically, the time to retrieve from the inverted index grows linearly. So let's say you match, you have 10 million data objects and you match 90% of them, then you still need to sort of retrieve 9 million IDs. And an ID, as we said before, is 8 bytes on disk. So you're basically talking about loading 9 times 8, 72 megabytes of data into memory, which doesn't sound that much, 72 megabytes, but we're talking about like millisecond latencies here. And then the allow list that we talked about before, that needs to be efficient for lookups, because otherwise, if we have a list that's just, let's say it was just an array, and then you have to sort of do a search on that array again. So there we need a mechanism that's efficient for lookup, which is why we're currently using a hash map. And that takes time to build up again. So there is a cost to this in the inverted index. And this is currently a major focus of what we're optimizing. Just in general, make this more memory efficient, make sure that we have fewer memory allocations and it's faster, so that there's less pressure on the garbage collector. So yeah, we don't quite see in very large cases, we don't quite see the query times that we would like to see yet. And there are a few sort of targets where we want to get to that would just enable completely new use cases, which I think is super cool. So there are cases where the inverted index can be the bottleneck, but this is something that we're currently working on. And it's, from an engineering perspective, it's boring optimization, so to speak, because the approach is the correct one. We just need to make it faster.
Super cool. So going from the neurosymbolic filters where you're checking it with the inverted index and is it contained in the set, if we're now stacking vector searches, so let's say we're doing an image search and I want to give you 2 images as an example to find the third image in the set, are we going to do a similar approach where we have two vector distances for each of the images?
Yeah, you could do both approaches basically. I mean, you can send off 2 separate searches, and you can just say, this is the results for search 1, this is the results for search 2, and now I need to merge them somehow. That is going to be very accurate, but at the same time, it's also, I mean, if you do it with 2, then you have 2 searches, so your search latency is basically twice as much. If you say, I want to do this with 100, and maybe their text is a bit more interesting, because you could say, well, I want to search for this paragraph of text, which is really 10 sentences. Then if you do 10 searches on each sentence, then you already have 10 searches. So this builds up quickly. But since they're vectors, you can, of course, also just take the mean of the 2 vectors and just do a single search.
Mm-hmm. So that takes us into our next topic that we had on the Slack chat, is going beyond 512 tokens when you're encoding these long documents. Things like sentence BERT are limited to 512 tokens. And I incorrectly had suggested using, say, Big Bird, which attends over 4096, or say K9, which hashes out the character encodings. But I forgot that these aren't trained with the, say, Siamese network contrastive learning encoding. So you can't really currently use these things like sparse transformers, recurrence transformers, these long range attentions, because they're not trained for this objective. And I remember this back when they were looking at BERT and saying BERT doesn't really produce great sentence embeddings, even though it can do squad and glue benchmark tasks. So the current approach is averaging out the vectors. And can you tell us a little more about the problem where, as you mentioned in the Slack chat, where you get one sentence that's just like one word, because articles can be written pretty casually. So if you split it like that, you end up with that kind of problem.
Yeah, exactly. So if the data set isn't very clean, then sometimes you just have these sort of nonsense matches, which isn't really a problem if your query is good, because then your good query probably matches a good object. But if you get into a situation, so what we saw there on a case, this was with a sentence transformer model. I don't know which one, but I assume this is similar for similar models. The user tried putting in a sentence, sort of a regular sentence that had a good meaning, and then used another sentence or just a partial sentence, which was basically just the word however. And then because we're splitting on the sentence level, and this is just to give the background, you mentioned those limits of 512 tokens. So the idea is that if you want to throw a really large document at Weaviate, then we can't just say, well, we can't use this transformer model because it's more than 512 tokens. So the simple way is to just say, okay, how can we chunk this document up into smaller parts? And this is the easiest or the most obvious when there is the sentence level. And then, we get, let's say, maybe 100 sentences where we can be pretty sure that each sentence is less than 512 tokens. And having said that, there might be better ways. That could be maybe the paragraph level would be a better way or something. So this is definitely something where I could see more configuration options in the future to just make that more configurable. But yeah, so what we're seeing right now with this query where we have a good sentence and then just a single word, because we take the mean of both sentences, we would assume that sentence 1 has a very good sort of meaningful vector position. And if sentence 2 was a real sentence, we'd probably have the same. And then getting the average of those would probably be good, because it would be sort of combining the two, as you said also on Slack. We would expect that they're orthogonal to each other. So we could assume that we can just encode both pieces of information in that single vector. But the problem is, because the second sentence doesn't really have a lot of meaning, it just sort of, it's somewhere which is nonsense in the space. And then we give a lot of weight to this thing because it's 50-50, because there's just two sentences. And on its own, that might not be a problem yet. But now if you have similarly, sort of unclean data in your data set, and in this particular data set, I think the user literally had a sentence that was just called however, or something like that, or maybe, however, and another words, but sort of similarly very little semantic meaning. Then by giving so much weight to that second sentence in the search query, we started finding those nonsense objects there as well. So I think this is a case where if we simply didn't do any averaging, then the sentence transformer model would have just ignored that second however, because it could have sort of seen the entire sentence and looking in both directions, you could say, okay, this additional word doesn't add any meaning. But because we forced it to sort of look at this in isolation, we're now giving it more meaning that it really has. And I think this is something where we could benefit a lot from, just more configuration options where you say, well, in this case, it's less than 512 tokens, don't split it up.
Yeah, super interesting. I would bet my research interest is data augmentation. I love the ideas of trying to form new ways of representing data through like context augmentation. So my personal bet on this would be, it would be better to have some kind of neural module that is trained to aggregate these sentences rather than try to somehow encode like 4096 and so on tokens, because it sounds like with the sparse transformers and then contrastive learning, I think that might be harder than, say, having something like, there's an algorithm called GPT-3 mix-up that I'll show on the screen in the podcast. And that's a technique for using, say, GPT-3 to combine two different data points for the sake of data augmentation. I think that might be the best way to go about combining these different sentences for the sake of producing the most semantic vector. So you have a really cool idea of encoding these long contexts, and definitely something that will be important for, say, looking at videos, biological sequences, and all sorts of the other data domains that Weaviate is taking on. So sort of to wrap up the podcast, I think that Weaviate will really help anyone out there understand knowledge graphs better. And it's a very interesting way of looking at these GraphQL schemas. So just maybe every week in our vector search show, want to touch on knowledge graphs and kind of get Etienne's view and try to distill his understanding of it to maybe, deep learning researchers and more people and myself, to try to just get a better sense of what's going on with knowledge graphs. So what's your inspiration for knowledge graphs? How do you currently see them and the application of them?
Yeah. So before we moved into the direction of a vector search engine, we actually called Weaviate, I think, something like the decentralized knowledge graph, because that was really the direction that we wanted to go into. And at that point, it was really hard to just find a proper definition of what a knowledge graph actually is. And the examples that people could come up with is like, well, if you search something on Google, then maybe you find a person and that person has a job, and then sort of from person to job, that's a relation. And now we're talking about a graph, and because you're representing knowledge, then basically sort of this is a very simple definition of what a knowledge graph potentially might be. And for me, when looking at Weaviate, I think there's two different perspectives that we can look at. One is if we maybe ignore the deep learning aspect of it for a moment and just say, well, we just have these entities and they're connected. In Weaviate, you can make those graph-like connections, and Weaviate is not a graph database. So they're like, if you're trying to go for let's say shortest path algorithms or something, you'd be disappointed. And I'm a big fan of using the right tool for the job, and in this case, a graph database would just be the right tool for the job. But nevertheless, it can help you just representing your data. If you know your data is linked, then by all means do set that cross-reference link in Weaviate as well to keep that connection alive. And without sort of any kind of vector search or any deep learning magic, you can still just, if you have that relationship in your data, you can retrieve that relationship later. And now if you have those relationships and then you sort of use vector search on those objects that you already have, one of the interesting things that you can do is that you can basically combine, for example, a text embedding space and an image embedding space without having a model that actually is capable of that. So you have a separate text model and you have a separate image model. They produce their own vector spaces, which are not compatible, but still you can just link them in Weaviate. So let's say you search for car, and then for car, it's linked to an image of, I don't know, a black Porsche or something. And then that you do a similarity search, and that maybe is similar to a, let's say, black Tesla. And that has the connection again to the Tesla object. Then now you've basically sort of done this text image similarity search where you started with text, ended up at text again, but actually what you did is a similarity search on images. And this is, I think, something that's super cool, because this very simple tool of just connecting data point A to B sort of lets you connect things in different vector spaces. And this is the one side of looking at knowledge graphs. And then I think the other side is a completely different approach, where you say you have this existing graph and you just train a model to come up with embeddings that represent those graph connections. And I think this is what the PyTorch Wikidata one is about, where you have those connections in Wikidata, which would also be similar to this. This is a person. The person maybe has an occupation actor, and they start in this particular movie. Then if you just train embeddings on this, what you can do is do a nearest neighbor search again on these objects. And then if you search for a specific actor, for example, and you just get the nearest neighbors, then you would find all those different entities, like the movies that they starred in, or the people that they acted with, or the producers, and these kind of things.
Yeah, that's awesome. Those are two such interesting ways of thinking about knowledge graphs. The first one, the multimodal knowledge graphs, it's such an interesting thing. I had never thought about this idea of I always thought of just entities and say like was in, movie, these kind of relations, but thinking about connecting images, and then you ask, well, how do you add an image to a knowledge graph? You use the vector embeddings, and it's pretty interesting, that idea. And then the second one, the idea of using the structure bias, and we talk all the time about inductive bias and architecture bias in deep neural networks, and having that structure that lets you exploit that like linguistic structure, I guess, of having that to learn better representations. Just two extremely interesting ideas, and a topic that we're going to come back to every week on the Vector Search Show, at least something about knowledge graphs and building up that understanding.
Nice. We should also definitely have Bob as a guest on the podcast at some point then, because I think he really loves these graph embeddings and anything to do with the graphs. And I think he definitely has more knowledge graph use cases in mind than I do. Or I'll just sync up with him to get some new ideas for every week.
Super cool. Yeah, it'd be great to have Bob on the podcast, and Laura and the rest of the Weaviate team, and coming into the Vector Search Show. So thanks everyone for watching the first episode of our Vector Search Show. Hopefully, as we iron it out and get our first or a second podcast together, but our first run of our new specific topic of trying to take down these topics that we have from the Slack chat. So again, the Slack chat will be linked in the description of the video if you want to join in, and if you have an idea, we will read it and then talk about it further here. So thanks for listening.
Yeah, thank you for having me, and thanks for this great idea. I'm really looking forward to just seeing where this is going.